So last time we talked about area in polar coordinates, and today it's about length. Now, the thing is, we don't want to have to go through and reinvent the wheel every time we go do something. We say, is there anything that we can fall back on that we can say, well, if I can reduce it to something I've known before? And the answer is parametric curves. So I can take any polar curve, and I can think of it as a parametric curve. Now, oftentimes when we think of parametric curves, we think of it as x is a function of t, y is a function of t. This says, well, you have something very similar. But now, instead of being functions of t, which we often think of as time, these are going to be functions of theta. So we can say, well, our polar curve becomes x equals r cosine theta, y equals r sine theta. This is our basic, how do you convert between polar and parametric, polar and Cartesian. And then we say, well, we're on r equals f of theta, so we have x equals f of theta cosine theta, y equals f of theta times sine theta. And now we say, well, we know the formula for arc length in parametric. You integrate from where you start to where you stop, in our case from alpha to beta. You take the derivative of the x prime with respect to its variable squared, derivative of y prime with respect to its variable squared. So we just go through the process. We're taking the derivative of f of theta cosine theta, product rule, f prime times cosine, and then it'll be f times the derivative of cosine, which is negative sine. For y, f prime times sine plus f times the derivative of sine, which is cosine. Now, at this point, it looks terrible, and we're going to make it look worse. But sometimes, as an intermediate step, it looks bad for just a moment. So we square things out. So if you're very patient and you square things out, you'll see certain things emerge. So for instance, when you look at the f prime squared, there's a cosine squared and a sine squared. You also will see that there's an f squared, and here there's a sine squared, there's a cosine squared. Then you get your cross terms. Namely, if you square a plus b, you get 2ab. So you have your 2, your f prime of theta, f of theta. From here you'll get cosine times negative sine, and from here you'll get sine times cosine. And now, lo and behold, it all of a sudden becomes really beautiful. Cosine squared and sine squared becomes 1. Minus cosine times sine plus cosine times sine becomes 0. And it reduces to the formula. So you integrate from your starting angle to your ending angle, the square root of f prime squared plus f squared. That's it. That's the whole formula. All right. The rest of today is practice. So, any questions before we get into practice? All right, well then, let's begin. So we'll start with a nice, easy warm-up. Find the length of the cardioid, r equals 1 minus cosine theta, where theta goes between 0 and 2 pi. This is a very standard example. This is oftentimes one of the first things we learn about when we talk about polar curves, because it's like, this is kind of a cute curve. It's the kind of curve we'd have a hard time doing if we were doing Cartesian coordinates. Well, let's make it a little bit easier on ourselves. How about, instead of going from 0 to 2 pi, we can use symmetry and just say, if we went from 0 to pi, it's the same as pi to 2 pi. So let's just go from 0 to pi and double it. That might or might not help, but oftentimes if I can knock a problem down in size, I like to do it. So 2 integral 0 to pi, square root of, now it's time to see if you remember. What comes next? Okay, so take the derivative. All right, what's the derivative of 1 minus cosine? It'll be sine. So we're going to get sine squared. Plus, now what? Yeah. the function 1 minus cosine theta squared, d theta. Okay, well, that's not looking so bad. Okay, well, let's see what that becomes. 0 to pi, and we expand. So that's sine squared theta plus 1 minus 2 cosine theta plus cosine squared theta. What can we do? Okay, so cosine squared and sine squared can combine, becoming 1. We already have another 1, so that's like a 2. So let's see, we have 2 integral 0 to pi square root of 2 minus 2 cosine theta. In fact, we can even pull the 2 out, all the way out in front. But when we pull it out of the square root, it'll become a square root of 2. So 2 square root of 2 integral 0 to pi, the square root of 1 minus cosine theta. I regret doing that, but oh well, I made a commitment. I'll stick with it. All right, now, how do we handle that? We did do these types of integrals before. And I'll tell you that there were 2 things that we said you could do in this case. One thing you could do is use conjugates. The other thing you could do is power reduction. And you're probably thinking, no, you can't. There's no squares in there. Well, the thing about equations is they work both ways. Okay, which one do you want to do? Power reduction? Okay, so why does power reduction relate at all? Well, let's remind ourselves what our basic formulas for power reduction are, because in polar coordinates, they get used a lot. So you want to make sure you know these. So for instance, what is cosine squared? Yeah. In fact, I'm going to, instead of cosine squared theta, I'm going to use cosine squared x. Just bear with me. 1 plus cosine 2x over 2. What about sine squared? What is that? 1 minus cosine 2x over 2. And now are sort of like, 1 minus cosine of something. There's a 1 minus cosine of something there. So I could rewrite this as 1 minus cosine of 2x is 2 sine squared of x. Now we're not quite there. We need to have 1 minus cosine theta. So what does 1 minus cosine theta equal? Two sine squared of theta over 2. Right, because we got to, essentially what we're doing is we're going to replace 2x by theta. Or another way of thinking of it is x is half of theta. So, if we use that, here we go. What do we have? Well, we have 2 root 2, integral 0 to pi, square root of 2 sine squared theta over 2, d theta. Again, you can pull that 2 out of the square root, and there's another square root of 2, so that brings us up to 4 in front. So 4 integral 0 to pi. What happens to the square root of sine squared theta over 2? It becomes sine theta over 2. Now, we've been bit before, so we're a little bit cautious about saying that. Why are we a little tiny bit nervous here? Yeah, you always have to wonder, do I need to worry about absolute value here? Why would we need to worry about absolute value? Because the square of the square root is the absolute value. When would it make a difference? If you had something negative. Now, let's think about it. We have sine of theta over 2. Theta is going from 0 to pi. Is that ever negative? No. So we're okay. All right, so we're close, because now we have something we can integrate. What does this integrate to? Well, the 4 is there. Integral of sine? Negative cosine theta over 2. Do I need anything else? Oh, we need a 2 or a half, apparently. If we average them, that's what? 1.5? 1 1/4? So which one do we need? Do we need the 2 or the half?
We need the 2.
Yeah, we need a 2 because we're going to be dividing by a half. Yes, good, good. So I'll put a little 2 out there. And then we need to evaluate 0 to pi. So let's see, this is 8 minus cosine of pi halves. Cosine of pi halves? 0. Minus cosine of 0. Yeah, so minus 1. Which says that our final answer is 8. It's actually kind of amazing because we're so used to seeing when shapes like this in polar coordinates, you see pi so often, you just take as a foregone conclusion everything should have a pi. Not necessarily. You never know. You never know. All right, so that's our first example, a nice warm-up. Okay, let's try a couple more. Find the length of the curve r equals root 5 e to the minus theta over 2, where theta goes between 0 and 2 pi. And so this is actually a picture of what the curve looks like. Not that we need to know what it looks like, but okay, that's what we're after. So what do we do? Well, probably won't surprise you. We're going to use the formula. All right, so integral 0 to 2 pi square root of, what comes next? Okay, so there's square root of 5 e to the negative theta over 2 times negative a half. And then we're going to square. Good. So I'll take the derivative, square it, plus the original function, square root of 5 e to the minus theta over 2 squared. All right. Well, let's see if we can't make a little bit of headway here. Well, what happens when I square this first term? What comes out? 5/4 e to the negative theta. In the second term, what comes out? 5 e to the negative theta. Okay. Now, certainly we can pull out the e to the negative thetas. So let's see, we have the square root of 5/4 plus 5 e to the negative theta. Now let's see if we can't take that and simplify it. First off, the square root of e to the negative theta, what will that become? E to the negative theta over 2. Let's think about the 5/4 plus 5. Well, if we wanted to simplify that, what should we do first to 5/4 plus 5? Okay, combine, common denominator. So the common denominator would be 4. That would be 5/4 plus 20/4. What does that make? 25/4. And if you take the square root of 25/4, you get 5 over 2. All right. Good. Progress. And now we're left with something that's not so bad to integrate. Ah, these are fun. Okay. All right. So what's the integral of 5/2 e to the negative theta halves. Well, the 5 halves, that's not so bad. What else? Yeah, negative 2, e to the negative theta over 2. Well, no, there's no d theta, but there is a 0 to 2 pi. Right, because you have to account for that negative half up in the exponent, negative half theta. So you divide by negative half, which is the same as multiplying by negative 2. So what do we have? Well, we have, this is a minus 5, and then we get, plug in 2 pi. 2 pi over 2 is pi, so that's e to the minus pi. Then e to the 0 is 1, so we have e to the minus pi minus 1. And that's our answer. Now, should we be nervous about this answer? It looks negative, right? And if we're to look after length, what should be true about our length? Should be positive. But, someone has said, but it's not negative. It only looks negative. Why is it not negative?
Because due to the negative pi, well, you know that something to a negative is going to make that number really small. And then your negative times negative, that's going to be the positive number. So your positive number is going to be the bigger number in that subtraction.
Okay, so the key is that e to the negative pi is actually fairly small relative to 1. So e to the minus pi minus 1 is itself a negative. There's another negative. And as we've learned since we were kids, 2 wrongs do make a right. Wait, that's not true. Okay, all right. So you could, if you wanted to make yourself feel better by making it look less than negative, you could write it as 5 times 1 minus e to the minus pi. And essentially just take this negative and move it inside. But it's the same number, it just looks more positive. So, all right, well, we have plenty of space left on this page, so we should do another one. Find alpha greater than 0, so the length of the curve r equals e to the minus alpha theta, where theta goes from 0 to infinity, has total length 13/5. So this is it's actually from an old final exam, but a really old final exam, back in the day. So one of the things you might notice here is that theta is going to infinity. So we're going to be spinning around not just once, not just twice, but infinitely often. And so the question is, even though we spin around infinitely often, is it possible to have finite length? Well, yeah, it is, as we're about to convince ourselves. This seems strange, but we're going to see stranger things. And not just that Netflix show. So wait till after break. All right. So let's figure this out. In fact, it doesn't look like it's going to be so bad, because it's very similar to the one we just did. So we're going to have a very similar setup. So we know that our total length is 13/5. So we're not actually going to try to find the length. We're given the length. We're going to try to figure out the right function. So it's one of these sort of like reverse the problem. But it's okay. We can handle that kind of thing. So we know that we have 13/5. That's our length. It's equal to, and I'll just write down the generic formula as a reminder, alpha to beta square root f prime of theta squared plus f of theta squared d theta. All right. So our bounds, 0 to infinity. Square root. What's the derivative of this function, e to the minus alpha theta? Yeah, negative alpha e to the minus alpha theta squared. And our original function is the function, e to the minus alpha theta squared, d theta. Okay, give ourselves some space as we move along here. 0 to infinity. And we square things. We get alpha squared e to the minus 2 alpha theta plus e to the minus 2 alpha theta. All right. Except that does not look like 2 to the alpha theta. That looks like 2 alpha alpha. There we go. 2 alpha theta. All right. Where do we go? No, we're not dropping this problem. We're getting all the points. Okay, so we can pull out the e to the negative 2 alpha theta. Okay, so integral 0 to infinity. And really, we'll just go ahead and say, look, well, the constant term is alpha squared plus 1. That'll be its own square root. And then the other term, that's the e to the minus 2 alpha theta. When I square root that, what does that end up being? E to the minus alpha theta. Have I been saying alpha? That looks suspiciously like an A now that I look at it. You know what? We're sticking with the alpha. I've committed. It's, you know, alpha was A before being A was cool. So, all right. D theta. Okay. You have to integrate that. Now, this square root of alpha squared plus 1, how do you integrate that? Yeah, you don't integrate it. It's just a constant. That just comes out in the front. So that's the square root of alpha squared plus 1. Good. But we do have to integrate e to the minus alpha theta. How do we do that? Yeah, negative 1 over alpha, e to negative alpha theta. Then we evaluate from 0 to infinity. All right. Now comes our time when we put on we actually have to deal with the infinity. And so it's like we're doing an improper integral because we're doing an improper integral. So that's why it feels like it. Now, the way we should do this is we should plug in infinity. Now, you can't really plug in infinity because, you know, infinity is not a number. But when we talk about plug in infinity, what we mean is what happens as we go to infinity. So the first part here, this alpha squared plus 1 and the square root and the minus 1 over alpha, those are numbers. We don't need to worry about those. It's the theta. So what happens to e to the minus alpha theta? And remember here, it's important to remember that our parameter alpha is positive. What happens to e to the minus alpha theta as theta gets big? Yeah, the whole thing goes to 0. Because what's going to happen is if theta is getting big, minus alpha times theta is getting to be a huge negative number. But that's what's in our exponent. So e to a large negative number is going to get small. So when you plug in infinity, of course, plug in, you're going to get 0. Subtract. Now we've got to plug 0 in. Well, what happens when I plug 0 into e to the minus alpha theta?
You get 1.
You get 1. So we're going to subtract this constant, which is minus the square root of alpha squared plus 1 over alpha. Well, minus, minus, that makes a plus. And now, after all that work, we come to the conclusion that the square root of alpha squared plus 1 over alpha has to equal, and we work our way back up here, 13 over 5. What should we do next? Sorry, what? You want a square? All right. People like to square things. Good. Get rid of the square roots. So, alpha squared plus 1 over alpha squared equals 169 over 25. Now what? I think I heard someone say cross multiply. And if not, I'm going to pretend like they did because that's what I want to do. So, we cross multiply just because fractions, they can challenge us. So, when we can get rid of fractions, it's a good idea to get rid of fractions. So, if we cross multiply, 25 alpha squared plus 25 equals 169 alpha squared. Well, I can move the 25 alpha squared across. 169 subtract 25. 144 alpha squared equals 25. Alpha squared should equal 25 over 144. That's looking promising. So now what? Take the square root and you get 5 over 12. Now somebody is going to say, wait a second, what about plus or minus? What's our response to those people? Why are you making it so hard? No, that's not our response. Our response is, we were told to find the one that's positive. So we can't take a negative one. So the answer is indeed 5 over 12. All right. Okay, next one. Find the length of the curve r equals secant to the fifth times 1/5 theta for 0 less than or equal to theta less than or equal to 5/4 pi. Interesting choices. All right. Well, let's see where this problem will take us. So, apparently we have a lot of space here, so it might be a fun problem. All right, so our length, integral from start to stop, 0 to 5/4 pi, the square root of, okay, something. Well, what goes here?
F prime theta.
All right, f prime theta, which is? Ooh, close. All right, it is indeed. We have had a suggestion. 5 comes down, secant to the fourth, 1/5 theta. And there was a 1/5. There will be a 1/5, but there's something in the interim that has to go before that 1/5. So what's the inside function? If we're thinking chain rule, if we have something to the fifth, what's our inside function? Secant. So if we're taking derivative of secant, we've got to write down secant tangent. Secant of what? 1/5 theta. Yeah, the inside is still pristine, untouched, like a wildlife preserve. Okay, but now we keep going. Layer upon layer, we work through the onion. Now we're to the point where we take the derivative of 1/5 theta, which is 1/5. And that, we're going to square. Plus, well, the good news is, we just write down the function again. Secant 1/5 theta squared d theta. Oh, thank goodness we had enough space. All right, so that's what we have to do. Now, there's a couple of things that are nice. Notice we have a 5 and a 1/5, so we can cancel, almost as if that had been planned to happen, because it was planned that way. And notice here, we actually get a secant to the fifth. So if we're careful here, and of course, we like to be careful, we have secant to the fifth, and that's being squared. So we can write that as secant to the 10th, 1/5 theta. Then we have the tangent squared of 1/5 theta, because that's also being squared, plus secant to the 10th, because we're taking something to the fifth, then squaring that, so that's going to take it 5 times 2 of 1/5 theta. Okay, now what? Okay, the secant to the 10th is common, we can pull it out, and then we can really pull it out. It's going to go all the way, right? Yes, it will. Okay, so what will that secant to the 10th pull out as? Secant to the 5th. Now, you could ask, is it possibly negative? Do I need to worry about signs? And I'll tell you the answer. you don't need to worry about signs. Here's why. Where does 1/5 theta go between? Look at our range for theta. Theta goes from 0 to 5 pi over 4, so 1/5 of that goes from where to where? 0 to pi over 4. And between 0 and pi over 4, secant is positive. I know that because between 0 and pi over 4, cosine is positive and secant is 1 over cosine. So I don't need to worry about absolute value. I know that some of you are worried about it, so I just want to assure you. Tangent squared of 1/5 theta plus 1. Now, we've got to figure out a way to handle that square root. Square roots are always challenging for us. What can we do there? We can do what? Oh, the inside here becomes a secant squared of 1/5 theta. And then we're taking the square root, so that's going to become another secant. So what we really have is secant to the 6 of 1/5 theta. Great, good. Now we're outside of our square roots. You get to integrate secant to the 6. How do we integrate secant to the 6? Carefully. It's a bunch of secant squareds. Okay, so definitely we like secant squared. Why do we like secant squared?
Because it's the derivative of tangent.
We like secant squared because it's easy to integrate, derivative of tangent. So we have our great moment. We come to here and we say, you know, this is sort of a callback. So if I pull off a single secant squared of 1/5 theta d theta, then we look at this part on the end and we think, happy thoughts. Because this is like the derivative of tangent. We'll fix that in a second, of the 1/5. Now, what would make this great? Well, what would be really cool is if we said, hey, this could be our du if we did what? Well, it would make a great du if all this were tangents. So, if somehow we could replace our secant to the 4th by something that looked like a bunch of tangents, life is good. Can we do that? Okay, so it's a long equal sign. 0 to 5 pi over 4. So, we'll do it sort of in two steps. So I'm going to think of this secant to the 4th as secant squared. Because secant squared has a lot of uses. Now, why to think of it as that way? Well, we're going to use an identity which we've actually already seen, namely this one. That allowed us to get rid of that tangent squared plus 1. Now we're going to put it back. Tangent squared 1/5 theta plus 1 squared. Secant squared 1/5 theta. Now we say, let's make our substitution. So, this part is in terms of tangent. That makes us happy. This is almost the derivative of that. So, we'll let u equal tangent of 1/5 theta. What is du going to become? Secant squared of 1/5 theta, and then? And there's a 1/5, and there's a d theta. That's almost what we have here, so we're going to take this 1/5 and move it across and put it there. So, making our substitution, we get the integral. Let's do the bounds. Theta equals 0. Tangent of 1/5 times 0 is 0. Theta equals 5 pi fourths. 1/5 times 5 pi fourths? Pi over 4. Tangent of pi over 4? Is 1. Oh, somebody worked hard to get that. U squared plus 1 squared. And then the rest of that becomes 5 du. Now we're getting happier. We're like, oh, that looks pretty good. We're not quite there. What's the next thing for us to do? Yeah, we need to expand it a little bit. So, integral 0 to 1. We'll go ahead and put the 5 way out in front. Then we'll get u to the 4th plus 2u squared plus 1. And now we're ready to integrate. So we have the 5. Integral of u to the 4th. 1/5 u to the 5th. Integral of 2u squared. 2/3 u cubed. Integral of 1 is u. Evaluate from 0 to 1. The nice thing is when you plug in 0, you get 0. So we just have to plug in the 5. And so we get 5 times 1/5 plus 2/3 plus 1. Now if you multiply the 5 through, that becomes, well, you get 1, because 5 times a 5th, and then you'll get 5 more, so that's 6 plus 10 over 3. But of course 6 is 18 over 3 plus 10 over 3 gives us 28 over 3. That's not so bad. That's almost doable. In that we did it. All right, good. Okay. Set up, but do not evaluate. What? You're depriving us of the pleasure of not evaluating? Probably because it's not going to be very pleasurable to do it. An integral that finds the length of the Archimedean spiral. So this is the Archimedean spiral, r equals theta. Famous for Archimedes, who is considered one of the 3 great mathematicians. Archimedes, Newton, Gauss. All right. Of course, there's the famous legend of how Archimedes died. He was sitting on the beach doing some math homework. And a Roman soldier came along and said, "Stop doing your math homework." And he said, "No, I'm going to do my math homework." And so they killed him. So that's dedication for you. He was committed. So he would have gotten an A in calculus. All right. Well, all right. So this is actually going to be there's not a lot for us to do. What happens? Well, length is the integral, starting angle to ending angle, 0 to pi. The square root of, what comes next? 1, because the derivative of theta is 1. And you square that plus theta squared, and then d theta. All right, so that's the whole problem. We've set it up. Now, you might be wondering, why does it tell us not to evaluate? Well, the square root of 1 plus theta squared is unpleasant. If you were to do this, let's just sort of think of what would happen. What would be the right substitution? What's the right technique to use? Now, this is one where you kind of have to go trig substitution. The right substitution to make would be theta is what? Tangent of some other thing, so like tangent of t. If you do that, the derivative of tangent gives you a secant squared here. The square root of 1 plus tangent squared gives you another secant, making this a secant cubed. Secant to an even, you can hear the angels singing. Ah. Secant to an odd, you hear the devils rejoicing. So we're not going to do it, because secant to an odd, no, terrible. We're not doing it. All right, then there's this problem, which I know is very similar to the quiz problem, but you know what, we have time. Let's talk about it. Set up, but do not evaluate an integral that finds the surface area. That results when the Archimedean spiral r equals theta for 0 less than or equal to theta less than or equal to pi is spun around the x-axis. And I don't know why it says x is equal to an axis. That should be a hyphen. All right. What's the key word here? Yeah. Probably some people are, the key word is do not. Okay, no. Surface area is really what I want to draw attention to. Now, you can tell it's really important because they even italicized it, made it fancy letters. Another keyword, of course, is the setup. We're not actually going to find this, probably because it's not going to be a pleasant integral, but we don't know until we set it up. Even after we set it up, sometimes it's always not so clear which integrals are pleasant and which ones aren't. So let's talk about surface area really quick. It's good to remind ourselves, when we're doing surface area, what's our generic formula for surface area? Yeah, you integrate, because that means you're adding up little bits of surface, and what? 2 pi, and then there's two other things. Right, radius, length. That's it. Every surface area formula looks like that. You just have to adapt it to the right setting. So our setting is we're in polar, so we just have to think about what things become in polar. Now, very conveniently for us, we have this picture here. So we'll come back to this picture. We're spinning around the x-axis, which means we're spinning this way. So let's go through it. A to B will be 0 to pi. The 2 pi in polar will become, it's still 2 pi. It's a number. It doesn't become anything. It's just what it is. Come on. Be serious. Okay, now the part where we have to think. The way that surface area works is you say, here's a little bit of my piece of the curve. So just that little tiny piece. The radius says, how far is that piece from where you're spinning? So this is our radius. So how far is it from our little piece that we're spinning down to where we're spinning? Well, some people, I've heard several answers. Theta, I've heard arc length, I've heard theta sine theta. I was hoping for something a little bit simpler. Why was I hoping for something simpler? Because it was going to be, no. Yes, I was hoping for the y. Okay, this is y. If you ever want to drop down to the x-axis, how far you are from the x-axis is y. It might be negative y if you're below it, but it's y. Okay, so you're probably thinking, cool, totally wrong coordinate system, Steve. But yes, but it's the right idea. Now you just got to convert it to the right coordinate system. So, what does y become? R sine theta. That's our rule from going from the Cartesian to polar. But what is r for this curve? Theta. So this distance we drop down is theta sine theta. Okay, so that's the radius. Now, the length. How do we find the length? And the answer is we look over at our neighbor's work and said, hey, I can't help but notice you're doing something similar. I'm just going to copy you. I don't recommend you do that, by the way. But the length it's the length formula. So it's the square root of 1 plus theta squared d theta. And now, what comes next? Yeah, we're done. Because we're set up, but do not evaluate. And if you see an instruction on the exam, do not evaluate. Or you might even see something like, set up only, exclamation mark, exclamation mark. That's also a clue. Just set it up. All right. And then, actually that's it. We're done. We've learned everything. We must be ready for the test.